And now in this lecture we'll answer two questions. On both questions we'll find out the area of a shaded region. So we'll start with the first question. In the drawing we have the big quarter circle AOB. Inside this big quarter circle AOB we have this semicircle and this small quarter circle. Again our task is to find out the size of this shaded area, or the area of this shaded region. It will give us the question that AO equals to 10 units in its length. That is to say, the radius of this big quarter circle AOB is 10. Therefore, OB is also the radius of this big quarter circle AOB is equals to 10 units in its length. We define the center of this semicircle. This point is point C. OB is the radius of this big quarter circle, but OB is also the diameter of this semicircle. If the diameter of this semicircle is 10, it means that the radius CB must be equal to 10 over 2, that is 5. The radius CO of this semicircle must be also equal to 5 units in its length. AOB is a quarter circle, and therefore this is a right angle. Likewise, this is also a quarter circle, and therefore this angle must be equal to 90 degrees in its size. We define the touching point of this small semicircle with this big quarter circle, of this small quarter circle with this big quarter circle. This point is point P. We define this point as point Q. We define this point as point S. This is the small quarter circle PQS that touches externally this big semicircle at this point. So we define their touching point. This point is point M. So the small quarter circle have an external edge with this big semicircle at point M. So here we can implement rule 10. Repeat quickly rule 10. According to rule 10, if two circles or semicircles touch each other externally, then the straight line that connects the circles together passes through their touching point. So in the drawing we have those two circles that touch each other externally. This point P. The center of this circle is here at point O. The center of this circle is here at point M. The straight line that connects the circles together is of course the straight line OM. And according to this rule 10, the straight line OM must pass through their touching point, that is point P. Again, the straight line OM must pass through point P, that is their touching point. Or OPM is one straight line. Again, according to this rule 10, OPM is one straight line. If OPM is one straight line, it means that OM in total must be equal to OP plus PM. Again, OM must be equal to OP plus PM. So we can implement rule 10 in our drawing. Those two shapes has an external edge between them, have an external edge between them at point M. The center of this small semicircle is here at point Q. The center of this big semicircle is here at point C. The straight line that connects the circles together is of course the straight line CQ. And according to rule 10, the straight line CQ must pass through their touching point, that is point M. Again, the straight line CQ must pass through point M, that is their touching point. So we join point C and Q together by straight line, and according to rule 10, the straight line CQ must pass through point M, that is their touching point. from the drawing it is very easy to see that indeed the straight line CQ passes through point M, that is their touching point, exactly according to rule 10. And according to rule 10, CMQ is one side line, and therefore CQ in total equals to CM. CM is the radius of this semicircle, that is 5, plus MQ. Last MQ starts from point Q, that is the center of this small quarter circle, and then at point M, that is the point on the quarter circle itself. This is exactly the definition of a radius. Therefore, MQ is the radius of this quarter circle. We'll define the radius of this quarter circle as x. So MQ equals to x. And because of the fact that according to rule 10 CMQ is one straight line, it means that CQ in total equals to CM, that is 5, plus MQ, that is x. So in total CQ equals to x plus 5 units in its length. CQ equals to x plus 5. In the next step, I'll copy the right triangle CQO in a new page, and we will implement on this right triangle CQO the Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. CQ, the hypotenuse CQ equals to x plus 5 according to rule 10. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right triangle COQ that I copied from the original drawing. In this right triangle COQ, according to the Pythagoras theorem, CQ squared, that is the square of the hypotenuse, is equal to CO squared plus QO squared. CQ is x plus 5, therefore CQ squared is x plus 5 squared. And it is equal to CO squared. CO is 5, therefore CO squared is 5 squared, that is 25, plus QO squared. QO is the missing side, so we'll leave this it is. Here we will subtract 25 from this equation 1, and we get that according to equation 1, x plus 5 squared minus 25 equals to QO squared. So according to equation 1, we actually found out that QO squared is equal to x plus 5 squared minus 25. In the next step, we will join points O and P together by a straight line. Point O is the center of this big quarter circle. Point P is the point of the big quarter circle itself. Therefore, OP is the radius of this big quarter circle. That is equals to 10 units in its length according to what is given in the question. So PO equals to 10. What is the length of QP? Point Q is the center of this quarter circle. Point P is the point of the quarter circle itself. Therefore, QP is the radius of this small quarter circle. This equals to X units in its length. So in the next step, I'll copy this right triangle PQO on a new page, and we'll implement on this right triangle PQO the Pythagoras theorem. Here by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, so first of all, I'll copy this right triangle QPO. Page. So actually, this is the right triangle PQO that I copied from the original drawing. In this right triangle PQO, according to the Pythagoras theorem, PO squared, that is the square of the hypotenuse, equals to PQ squared plus QO squared. So I'll write it down. This will be equation 2. So PO squared, that is the square of the hypotenuse, equals to PQ squared plus QO squared. PO is 10, therefore PO squared is 10 squared, that is 100. And it is equals to PQ squared. PQ is x, therefore PQ is x, therefore PQ squared is x squared plus QO squared. QO is the missing side, so we leave it as it is. So in total, according to equation 2, we should find out that 100 equals to x squared plus QO squared. Here we subtract x squared from this equation, equation 2. And find again that according to equation 2, QO squared equals to 100 minus x squared. This is according to equation 2. And according to equation 1, we have already found out that QO squared is equal to x plus 5 squared minus 25. So we have two equations for QO squared. Therefore, we get equation 3 that states that QO squared according to equation 1 must be equal to QO squared according to equation 2. So q all square according to equation 1 is equal to x plus 5 squared minus 25, and it must be equal to q all square according to equation 2. Q all square according to equation 2 is equal to 100 minus x squared. So in total, according to equation 3, we actually found out that x plus 5 squared minus 25 equals to 100 minus x squared. Here we will open the brackets of this expression, and we get that x plus 5 squared equals to x squared plus 5 squared, that is 25, plus 2 times x times 5, that is 10x, minus 25, and it is equals to 100 minus x squared. On this side of the equation we have 25 minus 25 is 0. After we cancel 25, in this side of the equation we left only with x squared plus 10x, and it is equal to 100 minus x squared. So according to equation 3, we found out that x squared plus 10x equals to 100 minus x squared. Here we will add x squared to this equation 3. And again, that according to equation 3, x squared plus x squared is 2x squared plus 10x equals to 100. And again, I should found out that according to equation 3, x squared plus 10x equals to 100. Here we will subtract 100 from this equation 3, and get that two x squared plus 10x minus 100 equals to 0. Here we will divide this equation 3 by 2, and finally get that according to equation 3, 2x squared over 2 is x squared, then x over 2 is 5x, and minus 100 over 2 is minus 50, is equals to 0 over 2. 0 over 2 is 0. So in total we should found out that x squared plus 5x minus 50 equals to 0. So this is the quadratic equation, and the general formula for a quadratic equation is as follows: ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we'll find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared plus 4 times a times c over 2a. In our specific quadratic equation, that is to say x squared plus 5x minus 50 equals to 0, the variable that we are looking for is x. X is the radius of this small quarter circle. The coefficient a equals to 1, the coefficient b equals to 5, and the coefficient c equals to minus 50. So we have all the data that is needed in order to find out the value of x, that is the radius of the small semicircle, or that is the radius of the small quarter circle. We just have to put this data inside this general formula for x. In this way we find out the value of the values of x. We do it now, and we get that actually that x equals to minus b. b is 5, therefore minus b is minus 5, plus minus square root of b squared. b is 5, so b squared is 5 squared, that is 25, minus 4 times 8 times c. So it is minus 4 times A. A is 1, so minus 4 times 1 is minus 4 times C. C is minus 50, so minus 4 times minus 50 is plus 200. So in total, minus 4 times A times C is plus 200. So in total inside the root we have 25 plus 200 over 2A. A is 1, so 2A is 2 times 1, that is 2. So in total we should find out that x equals to minus 5 plus minus. Inside the root we have 25 plus 200 is 225 over 2. So if I know the way that x equals to minus 5 plus minus, and the square root of 225 is 15 over 2. So in total we actually found out that x equals to minus 5 plus minus 15 over 2. So here we will have two solutions that are possible for x. X is the radius of the small quarter circle. The first solution for x is that x equals to minus 5 minus 15 over 2. Minus 5 minus 15 is minus 20, and minus 20 over 2 is minus 10. X equals to minus 10 according to the first solution for x. But because of the fact that x is the length of this radius of this small quarter circle, x is a length, and as a length it must be a positive number. Minus 10 is a negative number, and therefore it is incorrect solution. We cancel the solution for x and we take into account only the second solution for x. The second solution for x is that x equals to minus 5 plus 15 over 2. Minus 5 plus 15 is 10, and 10 over 2 is 5. So the second solution for x is that x equals to 5. That is to say, the length of the radius of this small quarter circle x is equal to 5 units. Our task is to find out the size of this shaded area, or the area of this shaded region. So what is the area of the shaded region? From the drawing it is very easy to see that the area of the shaded region in total must be equal to the area of the big quarter circle A or B. Minus the area of this semicircle, minus the area of this quarter circle PQS. Repeat again. The area of this shaded region in total must be equal to the area of the big quarter circle A or B minus the area of the semicircle minus the area of the small quarter circle PQS. Actually, it is very easy to see from the drawing that if you subtract from the area of this big quarter circle A or B the area of this semicircle and the area of this small quarter circle PQS, in total you will get the shaded area, or the shaded region. Okay. So what is the area of this big quarter circle A or B? Because of the fact that the radius of this big quarter circle A or B equals to 10, the area must be equal to pi r square over 4. R is 10, so it is pi times 10 square over 4. So the area of the quarter circle in total must be equal to pi times the radius square, that is 10 square over 4. minus the area of the semicircle. The radius of this semicircle is equal to 5. Therefore, the area must be equal to pi times 5 square over 2. So in total, the area of the semicircle equals to pi times the radius square, that is 5 square over 2. Minus the area of this small small quarter circle PQS. The area of this small quarter circle PQS must be equal to pi times the radius squared. The radius x is 5, so it is pi times 5 square over 4. So in total, the area of this small quarter circle PQS equals to pi times the radius squared, that is 5 square over 4. So the value of this expression in total is the area of the shaded region. That is the area that we are looking for in this question. Ten square is 100. So in total, in the numerator we have 100 pi over 4. Here we have 5 pi is 25. So in total, in the numerator we have 25 pi over 2. Here we will multiply both the numerator and the denominator of this expression by 2, and we get that 25 pi times 2 is 50 pi. So it is minus 50 pi over 2 times 2 is 4. So this expression, to multiply both the numerator and the denominator by 2, is equal to minus 50 pi over 4. And here we have 5 pi is 25, so in total the numerator we have 25 pi over 4. So here we take 4 as a common factor of those three expressions, and we get that here it is 100 pi, of course, 100 pi. In total we get that 100 pi minus 50 pi is 50 pi, and 50 pi minus 25 pi is 25 pi over 4. 4 is the common factor of those three expressions. So in total we should find out that the area that we are looking for this question, that is the area of this shaded region, is equal to either 25 pi over 4 square units in size, or in terms of numbers, is equal to 19.635 square units in size. And again, we should find out that the area of this shaded region, in total it is equal to either 25 pi over 4 square units in size, or in terms of numbers, it is equal to 19.635 square units in size. So we finished to answer on the first question. In the next step, I will present to you the second question and answer on the second question of this lecture. In the second question, we have the same task as in the first question. We have to find out the size of this shaded region, or the area of this shaded region. So in the drawing, we have two semicircles that intersect with each other at those 2 points. We know that AB, that is the diameter of this semicircle, is equal to 5 units in itself. This is the angle ABC, that is equal to 15 degrees in its size. Angle ABC equals to 15 degrees in its size. Again, our task is to find out the size of this shaded region, or the size of this shaded area. So, first of all, we will divide the total area that we have here into 3 parts. We define the size of this shaded region, that is the area that we are looking for in this question, as C. That is to say, the area of this shaded region is equal to C square unit in its size according to our definition. We define the intersection point between CB and this semicircle. This point is point M. we will define the area of this second part of this shape that is very similar to a semicircle SB. That is to say, it is equal to B square units in its size according to our definition. And finally, we define the size of this shape A and B as A. That is to say, it is equal to A square units in its size according to our definition. And because of the fact that it is given us the question that those two semicircles can go into each other, that is to say, semicircle AB can go into semicircle CB, because of the fact that they can go into each other, they must have also the same areas. That is to say, the area of this semicircle AB must be equal to the area of this semicircle CB. So, write it down. Repeat again, because of the fact that those two semicircles can go into each other, they must have also the same areas. That is to say, the area of semicircle AB must be equal to the area of semicircle CB. But what is the area of this semicircle AB? Semicircle AB consists of those two shapes, and therefore the area of semicircle AB must be equal to the sum of the areas of those two shapes that it consists of. Very simple. So in total, the area of this semicircle AB must be equal to A plus B, because A is the area of this shape and B is the area of the second shape. So in total, the sum of the areas of those two shapes is equal to A plus B. And again, we should find out that the total area of semicircle AB equals to A plus B. That is the sum of the areas of the two shapes that it consists of. And the area of semicircle AB equals to the area of semicircle CB. What is the area of this semicircle CB? Semicircle CB consists of those two shapes, and therefore the area of semicircle CB must be equal to the sum of the areas of those two shapes that it consists of. Very simple. That is to say, in total, the area of semicircle CB must be equal to B plus C, because B is the area of this shape and C is the area of this shaded area. That is the area that we are looking for in this question. So in total, the area of semicircle CB equals to B plus C. B plus C is square units in its size. So according to equation 1, we found out that A plus B equals to B plus C. Here we will subtract B from this equation. So B will get cancelled, and we left only with B will get cancelled. So we left only with A equals to C. Here, on this side of the equation we left with A, this side of the equation we left with C. So A equals to C. What is C? C is the area of the shaded region. That is the area that we are looking for in this question. And according to equation 1, A equals to C. So it is equals to the area of this shape ACB. That is to say, the area of shape ACB is equal to the area of this shaded region. So we just have to find out the area of shape A and B, and this will be the area of this shaded region is equals to C, because A equals to C. Repeat again, we'll find out the area of shape A and B, that is equals to A. And because of the fact that A equals to C, it will be equal to the shaded area, that is the area that we are looking for in this question. Okay. So, in the next step, we'll do a construction That is to say, from point M, we draw perpendicular on AB. So this angle equals to 90 degrees in size, and this angle also equals to 90 degrees in size according to our construction. We define the touching point of the perpendicular from point M and AB. This point is point Z. We define the length of perpendicular MZ as h. MZ equals to h units in its length according to our definition. In the next step, we will join points M and A together by a straight line. By joining points A and M, we create peripheral angle AMB. This is peripheral angle AMB. Peripheral angle AMB subtend on chord AB. Chord AB is the diameter of this semicircle. And according to rule 7, any peripheral angle that subtends on the diameter of the circle or semicircle must be equal to 90 degrees in its size. So I'll repeat quickly on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing, we have a circle. This is peripheral angle ACB that subtends on chord AB. That is the diameter of this circle, and therefore peripheral angle ACB is equal to 90 degrees in size. So according to this rule 7, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in size. So as I mentioned before, we can implement rule 7 in our drawing. Because in our drawing, we have peripheral angle A and B that subtend on AB, that is the diameter of this semicircle, and therefore peripheral angle A and B must be equal to 90 degrees in its size according to rule 7. In the next step, we will focus on the right triangle, triangle A and B. I will copy triangle A and B in a new page and we will analyze this triangle, triangle A and B. What is MZ? MZ is the height to the base AB. Again, if AB is the base, then MZ is the height to the base AB. So actually, this is the right triangle AMZ. This is the right triangle AMB. This is the comment from the original drawing. Repeat again that MZ is the height to the base AB. Because why it is the height? Because it's great 90 degrees with the base AB. We calculate the area of this right triangle AMZ, AMB in two different methods, and then we get a equation one that says that the area of triangle AMB according to the first calculation must be equal to the area of the same right triangle AMB according to the second calculation. According to the first calculation of the area of this triangle AMB, the area of this right triangle AMB equals to the base AB times the height MZ over 2. MZ is h, so it is the base AB times the height h over 2. So according to the first method of calculation, the area of this triangle A and B, it is equal to the base AB times the height edge over 2. It is given us in the question that AB equals to 5 units in its length. In the next step, we will find out the area of this triangle A and B according to the second method. The area of triangle A and B, it is equal also to the base AM times the height MB over 2. The area of this triangle A and B equals to the base AM times the height MB over 2. Here we have 2 on both sides of this equation, so 2 will get cancelled. We get that AB times H, AB is 5, so it is 5H. It is equals to AM times MB. And again, according to equation 1, we should find out that 5H equals to AM times MB. We will continue to focus on this triangle A and B. I've copied the triangle A and B in a new page, and we will continue to analyze this triangle A and B. So actually, this is the right triangle A and B that are coming from the original drawing. You know that AB equals to 5 units in its length. So in this right triangle A and B, sinus 15 degrees equals to MA over AB. So as you know, sinus 15 degrees is equal to AM or MA over AB. So sinus 15 degrees is equal to MA over AB. AB is 5, so AB by 5. So in total sinus 15 degrees equals to MA over 5. Here we will multiply this equation by 5 and finally get that MA is equal to 5 times sinus 15 degrees. We will continue to focus on this right triangle A and B. On this right triangle A and B, cosine 15 degrees is equal to MB over AB. So already known. Cosine 15 degrees is equal to MB over AB. AB is 5, so cosine 15 degrees is equal to MB over 5. Here we multiply this equation by 5 and finally get that MB is equal to 5 times cosine 15 degrees. And we already found out that MA is equal to 5 times sinus 15 degrees. According to equation 1, we actually found out that 5H equals to AM times MB. Five H is equal to AM times MB. Five H equals to AM times MB. So we will substitute AM in this equation 1 by 5 times sinus 15 degrees, and we substitute MB in this equation 1 by 5 times cosine 15 degrees. And we get that according to equation 1, five H equals to AM. AM is 5 times sinus 15 degrees times MB. MB is 5 times cosine 15 degrees. So in total we found out that 5H is equal to 5 times sinus 15 degrees times 5 times cosine 15 degrees. Here we will divide this equation 1 by 5, and we get that according to equation 1, 5H over 5 is H. So we have 5 times 5, that is 25, and 25 over 5 is 5. So in total, here we left only with 5, that is 5 times sinus 15 degrees times cosine 15 degrees. So according to equation 1, we found out that H equals to 5 times sinus 15 degrees times cosine 15 degrees. Here we'll use geometric identity that says that sinus 2A is equal to 2 times sinus A times cosine A. Again, according to this geometric identity, sinus 2A equals to 2 times sinus A times cosine A. Here we divide this geometric identity by 2, and get that sinus 2A over 2 is equal to sinus A times cosine A. And again, if you found out that sinus 2A over A equals to sinus A times cosine A. And use this geometric identity in order to find out the value of sinus 15 degrees times cosine 15 degrees. So according to equation 1, we actually found out that H equals to 5 times sinus 15 degrees times cosine 15 degrees. So H equals to 5, here we have sinus 15 degrees times cosine 15 degrees. According to this geometric identity, we get that sinus 15 degrees times cosine 15 degrees equals to sinus 2A. 2A is 2 times 15 degrees, that is 30 degrees over 2. So in total, we found out that sinus 15 degrees times cosine 15 degrees, according to this geometric identity, is equal to sinus 30 degrees over 2. So in total, according to equation 1, we found out that H equals to 5 over 2 times sinus 30 degrees. Sinus 30 degrees is 1/2. So in total edge equals to 5 times 1, that is 5, over 2 times 2, that is 4. So in total we should find out that edge equals to 5/4. So this is the perpendicular MZ, that is equals to edge, and edge equals to 5/4. In the next step, we'll define the center of this semicircle. This point is point O, and we will join points O and M together by straight line. By joining points O and M, we created center angle AOM. This is center angle AOM, center angle AOM. This is center angle AOM. Center angle AOM subtend on chord MA. Again, center angle AOM subtend on chord MA. Likewise, we have peripheral angle ABM. This is peripheral angle ABM. Peripheral angle ABM equals to 15 degrees in its size, and it is also subtend on the same chord called MA. And because of the fact that those two angles are both subset of the same chord called MA, the size of this center angle AOM must be twice as large as the size of this peripheral angle ABM that is subset on the same chord called MA. The size of this peripheral angle ABM is equal to 15 degrees, and therefore the size of this center angle must be equal to 2 times 15, that is 30 degrees. This twice as large. This is the size of this peripheral angle ABM that is subset on the same chord called AM. So therefore, according to rule 13, the size of this center angle AOM must be equal to 30 degrees. So repeat quickly on rule 13. According to rule 13, the center angle is twice as large as the peripheral angle that subtended. A center angle is twice as large as the peripheral angle that is subtended on the same chord. In the drawing, we have a circle. This is peripheral angle ACB. This is equals to 30 degrees in size, and it's subtended on chord AB. Likewise, we have center angle AOB that's subtended on the same chord called AB. And because of the fact that those two angles are both subtended on the same chord called AB, the size of this center angle AOB must be twice as large as the size of this center angle ACB that's subtended on the same chord called AB. The size of this peripheral angle ACB is theta, and therefore the size of this center angle AOB must be equal to 2 theta because they are both subtended on the same chord called AB. So we only implemented rule 13 in our drawing. Why? Because in our drawing, those two angles are both subtended on the same chord called MA. And therefore the size of this center angle AOM must be twice as large as the size of this peripheral angle ABM that's subtended on the same chord called MA. The size of this peripheral angle ABM is 15 degrees, and therefore the size of this center angle AOM that's subtended on the same chord called AM must be equal to 15 times 2, that is 30 degrees, according to rule 13. Okay, so our task is to find out the size of this shaded area. We have already found out that A equals to C. What is C? C is the size of this shaded area. What is A? A is the size of this area. AMB. That is to say, those two areas are equal to each other. According to what we have already found out in the beginning of the lecture, those two areas are equal to each other in their sizes. That is to say, A equals to C. So in order to find out the size of this shaded area, we just have to find out the size of this shape A and B, because they are equal to each other in their sizes. So just if we find out the size of this shape A and B, and it will be equal to the size of this shaded area, that is the area that we are looking for in this question. What is the size of this shaded area A and B? Shaded area A and B consists of this arc AM. So what is the size of this shape A and B? Shape A and B consists of two smaller shapes. It consists of this sector AMO. It also consists of this triangle MOB. And therefore, the size of this shape A and B in total must be equal to the sum of the areas of those two shapes that it consists of. That is to say, it must be equal to the area of this sector AMO plus the area of this triangle MOB. Okay, and this is equal in total to the size of this shaded area because A equals to C. Okay, so I write it down. So the size of this shaded area in total the size of this shaded region is equal to the size of this shape A and B because A equals to C. But what is the size of this shape A and B? Shape A and B consists of two smaller shapes. It consists of this sector AMO. This is the size of the first shape that this consists of. The rounded sign above AMO is the sign of a sector. It means sector AMO. So in total, it means that the size of sector A, the area of sector AMO. That is the first shape that the big shape AMP consists of, plus the area of this second shape. The second shape is actually triangle AMOB, plus the area of the second shape, that is the area of triangle MOB. Repeat again that the sum of those two shapes it is equals to the big shape A and B. But the big shape A and B equals to A and A equals to C. By finding the size of shape A and B, we'll find out the area of this shaded region because A equals to C. And therefore, in total, the area of the shaded region equals to the area of sector AMO plus the area of triangle MOB. What is a sector? A sector is a portion of a circle. The green shape AOB is a sector. It is a portion of this circle enclosed by two radii and arc AB between them. The two radii are also defined as the legs of the sector. Repeat again, a sector is a portion of a circle enclosed by two radii and arc AB between them. What is the area of this green sector AOB? The area of this green sector AOB equals to the area of the circle that contains the sector, that is to say pi r squared. R is the radius of this circle, times the angle between the legs of the circle, times the angle between the legs of this sector, that is theta, over 360 degrees. So, a sector is a portion of a circle enclosed by two radii and arc AB between them. The area of this sector equals to pi r squared times theta over 360 degrees. So we use this formula in order to find out the area of this sector AMO. What is the area of sector AMO? Because to the area of the circle that contains the sector is actually pi r squared. R is the radius of the semicircle times the angle between the legs of the sector, that is 30 degrees, over 360 degrees. Repeat again, if we found out that the area of this sector AMO in total equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 30 degrees, over 360 degrees. Plus the area of this triangle MOB. What is the area of this triangle MOB? We choose the base SOB. So it is the base OB times the height, H. Why H is the height? Because it creates 90 degrees with the base BO. If you extend BO, we get that H creates 90 degrees with the extended base BO. Therefore, H is the height of the base BO. So it is the base BO times the height H over 2. So in total, the area of triangle MOB equals to base OB times the height H over 2. R is the radius of this semicircle. Because of the fact that the diameter of this semicircle is 5, the radius must be equal to 5 over 2. So the radius OB is 5 over 2. Likewise, the radius AO is also 5 over 2. So actually found out that the base OB of triangle BOM is equal to 5 halves. So the triangle MOB equals to the base OB, that is 5 halves, times the height H. H equals to 5 quarters over 2. So in total, the area of triangle MOB equals to 5 times 5 is 25, over 2 times 2 is 4, and 4 times 4 is 16. So in total, the area of this triangle MOB is equal to 25 over 16 square units in its size, plus the area of sector AMO. R is 5 halves, and therefore R squared is 5 half squared. So pi r squared in total equals to pi times 5 halves squared times 30 degrees over 360 degrees. 5 halves squared is 5 squared, that is 25, over 2 squared, that is 4. So pi times 5 halves squared equals to 25 pi over 4 times 30 degrees over 360 degrees. 30 degrees over 360 degrees is 1 over 12. So in total, the area of sector AMO equals to 25 pi over 4 times 12, plus the area of triangle MOB, that is equals to 25 over 16 square units in size. So here we have 25 pi over 4 times 12 is 48, plus 25 over 16. 25 pi over 48 plus 25 over 16 in total is equal to 3.2 square units in size. Repeat again, we should find out that the area that we are looking for this question, that is the area of this shaded region, in total it is equal to 3.2 square units in its size. So we finished the answer on the second question. In the next step, I will summarize the lecture. We start with the repetition on the first solution of the first question, and then repeat on the solution of the second question. In the first question, our task was to find out the area of this shaded region. So in the drawing, we have the big quarter circle AOB. Inside this big quarter circle, we have two shapes. We have this semicircle. This is the first shape, and the second shape is this small quarter circle PQS. Again, our task is to find out the area of this shaded region. So first of all, it is given us the equation that AO equals to 10. AO is the radius of this big quarter circle AOB. So the radius of this big quarter circle is 10. BO is also the radius of this big quarter circle, that is to say it is equals to 10 units in its length. We define the center of this semicircle. This point is point C. AOB is a quarter circle, therefore this is a right angle. Likewise, PQS is also a quarter circle, and therefore this is a right angle. We define the touching point between the big quarter circle and the small quarter circle. This point is point P. We define this point as point Q. We define this point as point S. Those two shapes have an external between them at point M. That is to say, they touch each other externally at point M. Whenever we have an external edge between two shapes, we can implement rule 10. So I repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects the centers together passes for their touching point. So in the drawing you have those two circles that touch each other externally. This point P. The center of this circle is 0 at point O. The center of this circle is 0 at point M. The straight line that connects the centers together is of course the straight line OM. And according to this rule 10, the straight line OM must pass for their touching point, that is point P. Again, the straight line OM must pass for point P, that is their touching point. Or OPM is one straight line. If OPM is one straight line, it means that OM in total must be equal to OP plus PM. So we can implement rule 10 in our drawing. Why? Because in our drawing, the big semicircle touch this small quarter circle externally at point M. The center of this small quarter circle is at point Q. The center of this big semicircle is at point C. The straight line that connects the centers together is of course the straight line CQ. And this straight line CQ must pass for point M, that is their touching point. For CMQ is one straight line according to rule 10. If CMQ is one straight line, it means that CQ in total must be equal to CM. CM is the radius of this semicircle, that is 5, plus MQ. MQ is the radius of this small quarter circle. We define the radius of this small quarter circle as x. Therefore, MQ or QM equals to x. So in total, CQ equals to x plus 5. According to rule 10, CQ in total equals to x plus 5. So actually join point C and Q together by straight line, and you can see that the straight line CQ passes for point M. That is their touching point, exactly according to rule 10. We just found out that CQ in total equals to x plus 5. So in the next step, I copied the right triangle COQ in a new page, and we implemented on this right triangle COQ the Pythagoras theorem. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. This is the right triangle COQ that I copied from the original drawing. This right triangle COQ, according to the Pythagoras theorem, CQ squared, that is the square of the hypotenuse, equals to CO squared plus OQ squared. CQ is x plus 5, therefore CQ squared is x plus 5 squared, and it is equals to CO squared. CO is 5, therefore CO squared is 5 squared, this is 25, plus OQ squared. OQ is the missing side, so we leave it as it is. So in total, according to equation 1, we can find out that x plus 5 squared equals to 25 plus q all squared. Here we subtracted 25 from this equation, and finally found out that x plus 5 squared minus 25 equals to q all squared. or QO squared, according to equation 1, QO squared equals to x plus 5 squared minus 25. In the next step, we join points O and P together by a straight line. Point O is the center of this big quarter circle, AOB. Point P is the point of the big quarter circle itself. Therefore, OP is the radius of this big quarter circle that is equals to 10 units in itself, according to what is given in the question. Notice the definition of QP. QP is, of course, the radius of this small quarter circle that is equals to x according to our definition. So in the next step, I copied the right angle PQO in a new page and implemented the Pythagoras theorem on this right angle PQO. This is the right angle PQO that I copied from the original drawing. This right angle PQO, according to the Pythagoras theorem, PO squared, that is the square of the hypotenuse, equals to PQ squared plus QO squared. PQ is 10, therefore PQ squared is 10 squared, that is 100, and it is equals to PQ squared. PQ is x, therefore PQ squared is x squared plus QO squared. QO is the missing side, so we leave it as it is. So in total, according to equation 2, we should find out that 100 equals to x squared plus QO squared. Here we subtracted x squared from this equation, and finally found out that QO squared equals to 100 minus x squared. This is according to equation 2. But according to equation 1, we already found out that QO squared equals to x plus 5 squared minus 25. So we have two different equations for QO squared. Therefore, we created equation 3 that says that QO squared according to equation 1 must be equal to QO squared according to equation 2. QO squared according to equation 1 equals to x plus 5 minus 25, and it must be equal to QO squared according to equation 2. QO squared according to equation 2 equals to 100 minus x squared. So in total, according to equation 3, we should find out that x plus 5 squared minus 25 equals to 100 minus x squared. We open the brackets of this expression and finally found out that according to equation 3, x plus 5 squared equals to x squared plus 5 squared, that is 25, plus 2 times x times 5, that is 10x, minus 25, and it is equals to 100 minus x squared. Here, in this side of the equation 3, we have 25 minus 25, that is 0. After we cancel 25, we left only with x squared plus 10x, and it is equals to 100 minus x squared. So in total, according to equation 3, we found out that x squared plus 10x equals to 100 minus x squared. Here we added x squared to this equation 3, and finally found out that according to this equation 3, x squared plus x squared is 2x squared plus 10x equals to 100. And again, according to equation 3, we found out that 2x squared plus 10x equals to 100. So here we subtracted 100 from this equation 3, and finally found out that according to equation 3, 2x squared plus 10x minus 100 equals to 2. Here we divided this equation 3 by 2, and finally found out that according to this equation 3, 2x squared over 2 is x squared, 10x over 2 is 5x, and minus 100 over 2 is minus 50, and it is equals to 0. 0 over 2 is 0. So in total, according to equation 3, we found out that x squared plus 5x minus 50 equals to 0. This is a quadratic equation, and the general formula for a quadratic equation is as follows. Ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus 4 of b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say x squared plus 5x minus 50 equals to 0, the variable that we are looking for is x. X is the radius of this small quarter circle PQS. The coefficient a equals to 1, the coefficient b equals to 5, and the coefficient c equals to minus 50. The only thing that is left to do is to put this data from a specific quadratic equation inside this general formula for x, and this way we will find out the value of the values of x. And again, x is the radius of this small quarter circle PQS. We did it, and we shall find out that x equals to minus b. B is 5, so minus b is minus 5 plus minus square root of b squared. B is 5, so b squared is 5 squared, that is 25, minus 4 times a times c. A is 1, so minus 4 times a is minus 4 times 1, that is minus 4 times c. C is minus 50, so minus 4 times minus 50 is plus 200. So in total, minus 4 times a times c is plus 200. So in total, inside the root, we have 25 plus 200 over 2a. A is 1, so 2a is 2 times 1, that is 2. So we found out that x equals to minus 5 plus minus 25 plus 200 is 225 over 2. The square root of 225 is 15. So in total we should find out that x equals to minus 5 plus minus 15 over 2. So here we will have two solutions that are possible for x. The first solution for x is that x equals to minus 5 minus 15 over 2. Minus 5 minus 15 is minus 20, and minus 20 over 2 is minus 10. 10 minus 10 is the incorrect solution because of the fact that x is a length. If x is the length, must be a positive number. Minus 10 is a negative number, so this solution is the incorrect solution. So we'll take into account only the second solution for x. According to the second solution for x equals to minus 5 plus 15 over 2. Minus 5 plus 15 is 10, and 10 over 2 is 5. So the second solution for x is that x equals to 5 units in its length. That is to say, the radius of this small quarter circle PQS is equal to 5 units in its length. Our task is to find out the size of this shaded region. So what is the size of this shaded region? From the drawing it is very easy to see that the size of the shaded region in total must be equal to the area of this big quarter circle AOB minus the area of this semicircle minus the area of this small quarter circle PQS. And again, the size of this shaded region in total must be equal to the area of the big quarter circle AOB minus the area of the semicircle minus the area of the small quarter circle PQS. It is very easy to see from the drawing that if you remove from the area of the big quarter circle this semicircle and this small quarter circle, we'll get the shaded area. Okay. So what is the area of the big quarter circle AOB? The radius of this big quarter circle AOB is 10, and therefore the area must be equal to pi r square over 4. That is to say, it is pi times 10 square over 4 minus the area of this semicircle. The radius of this semicircle is 5, and therefore the area of this semicircle must be equal to pi times 5 square over 2. So the area of the semicircle equals to pi times 5 square over 2 minus the area of the small quarter circle PQS. What is the area of the small quarter circle PQS? The radius of this small quarter circle, the radius x equals to 5, and therefore the area of this small quarter circle must be equal to pi times 5 square over 4. So in total, the area of the small quarter circle PQS is equal to pi times 5 square over 4. Here we have 10 square is 100, so in total in the numerator we have 100 pi over 4. Here we have 5 square is 25, so it is 25 pi over 2. We multiply both the numerator and the denominator of this expression by 2. 25 times 2 is 50 pi, 25 pi times 2 is 50 pi, and 2 times 2 is 4. So in total, this expression, after we multiply both the numerator and the denominator by 2, is equals to 50 pi over 4. And we have here 5 squared is 25, so it is 25 pi over 4. So here we took 4 as a common factor out of those three expressions. So in the numerator we have 100 pi minus 50 pi is 50 pi, and 50 pi minus 25 pi is 25 pi over 4. So in total we should find out that the size of this shaded region, in total it is equal to either 25 pi over 4 square units in size, or in terms of numbers, the area of this shaded region is equal to 19.635 square units in size. So we finished to answer on the first question. In the next step I repeat on the solution of the second question. In the second question, our task is to find out the area of the shaded region. So in the drawing we have two semicircles that intersect with each other at those 2 points. AB, that is the diameter of the semicircle, equals to 5 units in its length. And therefore the radius OA is 5 over 2, the radius OB is also 5 over 2. This is again ABC, this is equals to 15 degrees in size. And we also know that those two semicircles can go into each other, and therefore they must have also the same areas. That is to say, the area of semicircle AB must be equal to the area of semicircle CB, because they can go into each other. But what is the area of this semicircle? Semicircle AB. Semicircle AB consists of those two shapes, and therefore the area of semicircle AB must be equal to the sum of the areas of those two shapes that it consists of. We defined the size of this shape AMB as A, that is to say it is equal to A squared in size according to our definition. We define the size of this shape MB, the small semicircle is B. And therefore, in total, the area of this semicircle AB must be equal to the sum of the areas of those two shapes that it consists of. That is to say, it must be equal to A plus B. So, the area of semicircle AB equals to A plus B. And the area of semicircle AB equals to the area of semicircle CB because they can go into each other. Therefore, they must have also the same areas. We define the shaded area, the size of the shaded area, as C. That is to say, it is equal to C squared in size according to our definition. So, what is the size of this semicircle CB, or the area of this semicircle CB? The semicircle CB consists of those two shapes, and therefore the area of semicircle CB must be equal to the sum of the areas of those two shapes that it consists of. That is to say, it must be equal to B plus C. So the area of semicircle CB equals to B plus C. Here we subtract B from this equation 1. So here B will get cancelled on both sides of the equation, and we have only if A equals to C. So we found out that those two shapes, they are equal to each other in their sizes. That is to say, the area of this shaded region is equal to C squared in size. It is equal to the area of this shape A and B. Our task is to find out the area of this shaded region. Because of the fact that those two areas are equal to each other in their sizes, we just find out the area of this shape A and B, and it will be equal to the area of this shaded region because A equals to C. Okay. So in the next step, we join points A and M together by a straight line. By joining points A and M, we get that peripherical A and B. This is peripherical A and B. Peripherical A and B subtend are called AB, that is the diameter of this semicircle. And according to Rule 7, any peripherical that subtend of the diameter of the circle or semicircle must be equal to 90 degrees in size. Therefore, peripherical A and B is the right angle according to Rule 7. In the next step, we define the intersection point between CB and this semicircle. This point is point M. From point M, we draw perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point M and AB. This point is point Z. In the next step, I copied the right triangle AMZ, AMB. In the new page, we analyze this right triangle, triangle AMB. This is the right triangle AMB. This is the right triangle AMB that is coming from the original drawing. Again, MZ equals to H according to our definition. MZ is the height to the base AB. Why MZ is the height to the base AB? Because of the fact that MZ creates 90 degrees with the base AB. So MZ is the height to the base AB, and MZ equals to H. So this is the right triangle AMB that is coming from the original drawing. The area of this right triangle AMB is equals to the base AB times the height H over 2. Then again, the area of the right triangle AMB equals to the base AB times the height H over 2. Then we calculated the area of this right triangle AB according to the second method. The area of this right triangle AB also equals to the base AM times the height MB over 2. Is equals to the base AM times the height MB over 2. And it is very clear that the area of triangle AB according to the first method of calculation must be equal to the area of the same triangle AB according to the second method of calculation. Therefore, those two sides are equal to each other. We have 2 on both sides of this equation, so 2 will get cancelled. AB is 5, so we substitute AB by 5. So on this side of the equation we have in total 5H, and it is equal to AM times MB. 2 will get cancelled here, because you have 2 on both sides of this equation. So in total we found out that 5H equals to AM times MB according to equation 1. In the next step, I copied the right triangle A and B again in the new page, and we continue to analyze this right triangle A and B. This is the right triangle A and B that are coming from the original drawing. This is the angle ABM that is equals to 15 degrees in its size according to what is given as the question. So in this right triangle A and B, sinus 15 degrees, sinus 15 degrees equals to MA over AB. Sinus 15 degrees equals to MA times AB. AB is 5, so we substitute AB by 5. And finally found out that sinus 15 degrees equals to MA over 5. Here we multiply this equation by 5 and finally found out that MA equals to 5 times sinus 15 degrees. Likewise, here sinus cosine 15 degrees equals to MB over AB. AB is 5, so again cosine 15 degrees equals to MB over AB. AB is 5, so in total cosine 15 degrees equals to MB over 5. Here we multiply this equation by 5 and finally found out that MB equals to 5 times cosine 15 degrees. And we already found out that MA equals to 5 times sinus 15 degrees. We already found out that according to equation 1, 5H equals to AM times MB. So you can substitute AM by 5 times sinus 15 degrees, and substitute MB in this equation, equation 1, by 5 times cosine 15 degrees. We did it, and we can find out that in total 5H equals to AM, that is 5 times sinus 15 degrees, times MB, that is 5 times cosine 15 degrees. Here we divided this equation 1 by 5, so 5H over 5 is H. Here we have 5 times 5 is 25, and 25 over 5 is 5. So in total, in this side of the equation, we have to only 5 times sinus 15 degrees times cosine 15 degrees. So in total, according to equation 1, H equals to 5 times sinus 15 degrees times cosine 15 degrees. We have the geometric identity that says that, the trigonometric identity that says that sinus 2A equals to 2 times sinus A times cosine A. We divided this trigonometric identity by 2 and finally found out that sinus 2A over 2 equals to sinus A times cosine A. Again, found out actually that sinus 2A over 2 equals to sinus A times cosine A. We use this trigonometric identity in order to find out the value of sinus 15 degrees times cosine 15 degrees. According to equation 1, we only found out that H equals to 5 times sinus 15 degrees times cosine 15 degrees. So H equals to 5 times sinus 15 degrees times cosine 15 degrees. According to this trigonometric identity, sinus 15 degrees times cosine 15 degrees equals to sinus 2 times 15 degrees over 2. Sinus 2 times 15 degrees is 30 degrees over 2. So total sinus 15 degrees times cosine 15 degrees equals to sinus 30 degrees over 2. So total according to equation 1, we found out that H equals to sinus 30 degrees, H equals to 5 times sinus 30 degrees over 2. So H equals to 5 over 2 times sinus 30 degrees. Sinus 30 degrees is 1/2. So in total, H equals to 5 times 1 is 5 over 2 times 2 is 4. So in total, H equals to 5/4. This is the perpendicular MZ is equals to H, and H equals to 5/4 units in its length. Our task is to find out the size of this shaded area. We already found out that those two areas are equal to each other in their sizes. So we just have to find out the size of this shaded area is equal to the size of this area, the size of this shape, that is shape AMB, because C equals to A. This shape AMB consists of two smaller shapes. It consists of this sector AOM, and this is sector AOM, that is like a slice of pizza, plus this triangle MOB. So in total, the size of this shape, the big shape A and B, is equal to the sum of the areas of those two shapes that it consists of. That is to say, it is equal to the area of this sector AMO plus the area of this triangle MOB. Repeat again. The size of this shaded region is equal to the size of this shape A and B. This shape A and B consists of those two smaller shapes. That is the first shape, that is sector AOM, and plus the area of this second shape, that is triangle MOB. So total, the shaded area equals to the area of sector MAO plus the area of triangle MOB. So what is a sector? A sector is the green shape AOB is a sector. A sector is a portion of a circle enclosed by two radii and RKB between them. The two radii are defined as the legs of the sector. So the area of this sector AOB equals to the area of the circle that contains the sector, that is to say pi r square. R is the radius of the circle, times the angle between the legs of the sector, that is theta, over 360 degrees. Again, a sector is a portion of a circle enclosed by two radii and the RKB between them. And the area of this sector equals to pi r square times theta over 360 degrees. Use this formula in order to find out the area of sector MAO. What is the area of the sector MAO? It is equal to pi r squared. That is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 30 degrees, over 360 degrees. So actually, I skipped on the part that we have to join points M and O together by a straight line. By joining points M and O, we created a sine triangle AOM. Sine triangle AOM subtend on chord MA. Likewise, we have peritriangle ABM that subtend on the same chord called MA. And because of the fact that those two angles are both subtend on the same chord called MA, the size of this sine triangle AOM must be twice as large as the size of this peritriangle ABM. The size of this peritriangle is 50 degrees, and therefore the size of this sine triangle AOM that subtend on the same chord called MA must be equal to 15 degrees times 2, that is 30 degrees. Therefore, the angle between the legs of this sector AOM is 30 degrees. So we have to multiply it pi r squared times 30 degrees over 360 degrees. So in total, the area of this sector AOM is equal to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 30 degrees, over 360 degrees. Plus the area of the second shape that shape CBA consists of. The second shape that it consists of, it is triangle MOB. What is the area of this triangle MOB? It is equal to the base OB times the height to the base edge over 2. Why the height is edge? Because the extended base BO creates 90 degrees with edge. Those fingers are both right angles. So in total, the area of this triangle MOB equals to the base BO times the height edge over 2. So they have the second shape that the big shape A and B consist of. It is the area of this triangle MOB. They have triangle MOB equals to the base OB times the height edge over 2. R is the radius of this semicircle. R equals to 5 halves, because the diameter AB is 5, and therefore the radius must be equal to half of the diameter, that is 5 over 2. So OB is the radius of the semicircle, that is 5 halves. So R is 5 halves, and therefore R squared is 5 halves squared times 30 degrees over 360 degrees. OB is 5 halves, it is the radius of the semicircle, times edge. Edge is 5 quarters over 2. 5 times 5 is 25, 2 times 4 is 8, 8 times 2 is 16. So in total this expression equals to 25 over 16. So in total the area of triangle NOB equals to 25 over 16 square inches in size. Here we have 5 half squared equals to 25 over 4. So in total this expression equals to 25 pi over 4. 30 degrees over 360 degrees is 1 over 12. So in total this expression equals to 25 pi over 4 times 12 plus 25 over 16. 4 times 12 is 48, so in total in the denominator of this expression we have 48. So in total this expression equals to 25 pi over 48 plus 25 over 16. And the value of this expression in total, that is to say 25 pi over 48 plus 25 over 16 is equal to 3.2 square inches in size. So we shall find out that the area that we are looking for in this question, that is the area of this shaded region, in total it is equal to 3.2 square inches in size. Okay, thank you very much.